All right, welcome everybody. I don't think that too many people are going to sneak in. It's one of the bad things with these auditoria, these old ones, that people embarrass themselves by walking in front of everyone else. But we'll see. So welcome everyone to this lecture of our honorary doctorate, Gareth McKinley. I don't think that I have to introduce him. Most people here have probably heard more about him than about any other speaker that would come from a regular seminar that we have. So I will stop here. But I just wanted to thank Gareth up front. Most of you have probably seen the speech that he gave yesterday when the degree was given out. I have to say I'm slightly embarrassed that he probably represented rheology to the broader audience much better than Peter and myself did there. And I also like very much that you put rheology and theology now on the same level there. So I think this is going to stick behind. And I think that you're going to give a great talk here, convincing us even better that rheology is really something important in our life, but also related things there. So with that, I'll give the word to Professor Gareth McKinley, our honorary doctor.
Great. Thank you. Thank you so much, everyone, for coming. We're going to keep this very informal. Please put your hand up and ask a question if I say something that's not clear as we go along. Don't wait till the end, because then it's too late sometimes to understand. So you can tell that these pictures I took from the website are before I got my honorary degree, because the rector, Luke, pins something on you called an epitoga. This is a completely new word to me. Toga, of course, is a robe. Epi means on top of, like epidermis. I couldn't really wear it today, so here's my infra toga. So here you go. So this is what he pinned on me, but I'll keep it under my jacket for today. It's a great pleasure to be here. And what I'm going to try and tell you about today is not so much about rheology to start with, but about fluid mechanics, which is one of my other great loves. So whether you're a mechanical engineer or a civil engineer or a chemical engineer, we all have classes in fluid mechanics. And I want to tell you a little bit about how we can exploit some clever things with fluid mechanics to try and save energy through reducing friction. You all either walked here or cycled here, and so you all experienced frictional drag as you came here. And we want to talk a little bit about things that we can do maybe to help save energy in the future this way. Okay, so just to get introduce it to start, I'll talk a little bit about that to start with, and about how we're going to build structures to try and interfere with local fluid flow. And the particular design challenge I'm going to be interested in is going to be related to ocean engineering rather than aerodynamics. But it's going to be dealing with water, so water-based systems, and trying to make what we'll call a super hydrophobic surface to do that. And I'm going to explore a couple of different ways of doing it. First of all, passive meaning I don't have to put any energy in. And then we'll explore active ways of doing it using phase change and generating vapors. And then I will come to rheology towards the end, and we'll talk about active friction reduction using polymers. And if I don't run out of time, we'll try and think about maybe doing those two things together by the end of it. So that's what we're going to try and cover. Just to motivate you, if you were to look at a boat, if I was to plot the amount of energy that's consumed, so this is 100% of the energy, as a function of the speed of the boat, then actually on a boat on the surface, more than 50% of the energy that you put in is burned just in frictional drag, in just sliding the boat through the water. It's even more on a submarine, and that's because on a surface, some of it is associated with wave resistance. So you'll get dissipation, you'll get surface waves that are produced, but almost all of this comes from skin friction. It's the idea that the fluid has to get dragged along the side of the boat, and just pushing the boat through the surface of the water will consume something like about 60% of the power. So you might imagine that even if I only save 1% of that, then I'm going to save a substantial amount of energy. People have looked at many different ways of doing this. So here's some of the different ways that people have thought about doing it. And we're going to really focus on one particular class of things today. I'm not going to have time to tell you about all of them, but I'll at least mention some of these other technologies. One of them is called riblets. Another one is the idea of cavitation, of maybe producing a vapor phase very close. You may have heard of some particularly bad things that have happened with supercavitating torpedoes in the Russian Navy. So there's many different ways of doing this, but today, at least to start with, I'm going to focus on this one, and then we'll come back and think about polymer injection later on. Okay, so the goal is to try and lower this amount, something like 60 to 70% of the energy. The rest of it is in what's called hydrodynamic form drag. The fact that you have to push fluid out of the way, we can never change that. So we're always going to have some form drag, but if we can change this part, then we'll save some energy. And here's my motivation, if you want to be motivated by nature. So here's the object that we might be interested in trying to save energy on. And you'll notice in front of it, a dolphin quite happily swimming in front of this. It's actually riding the bow wave of the boat. But if you've ever had a chance to touch a dolphin, it feels slippery or slimy. It secretes a polymer coating that it actually uses to reduce friction. So this is our motivation. And people have looked at many, many different ways of doing this. So if you like molecular dynamics or things on the molecular scale, if you look at a hydrophobic surface, then it turns out that these are water molecules, that there's a lower density of water molecules near the surface. And so they're repelled from the surface. And so there's a thin layer. This is on the nanometer scale, though. So this is very, very small. Nature, in addition to dolphins, sharks are extremely good at reducing friction. And they actually, if you ever touch a shark, they don't feel slimy, they feel rough. And they feel rough because they produce these denticles, as they're called, but they're designed to interfere with the flow across the surface. And then in nature, we've tried to copy those things by putting things like riblets on surfaces, or even by trying to trap air in surfaces. And so the key goal of what we're trying to do is, if you've done a course in fluid mechanics, you'll be familiar with the parabolic velocity profile. And what we want to do is just interfere with the boundary condition very, very close to the surface. And I chose this slide to put here because Jonathan Rothstein was one of my former students and someone who's been here twice and stayed on sabbatical here. And so there's a nice connection with the Leuven group here. But the goal is to try and increase the velocity very, very close to the surface so that the fluid slides along the surface more easily. So before you're convinced at the end of this that this is going to save everything and that we're all going to save energy, there's many, many difficulties with these systems, including fluctuations, biofouling, and in general, durability is really the key limiting step at the moment. But I want to focus more on the fluid mechanics of what's going on. In terms of commercial applications, back in the 1980s, 3M actually were motivated by this idea of shark skin, and they actually developed a tape that you could actually stick onto planes. And this is an old plane. You'll notice the A320. This is back from the late 1980s. They demonstrated that it would work in principle, but then nothing happened. And for the next 40 years, engineers have really been trying to improve the viability of this. And it's really actually only very, very recently that BASF, together with Lufthansa, have actually been able to get this working on a commercial scale. So you may in the future be sitting on a plane at the airport, and you might look out of the window and you might see a plane like this, because just in December of this year, this actually achieved what's called type certification, which means that now they're actually going to put this skin on the surface of all Lufthansa and Swiss Air cargo planes. And all it does is reduce a 1% drag. Okay? But that 1% saves over 11,000 tons of CO2 per year and 3,700 tons less fuel per year. So just to give you an idea that engineers, even if we can just change things by a small amount, that can lead to a large change in terms of energy savings. And so this is an aerodynamic thing. By the way, this is the size of the plate that you have to put on. So this plane is actually covered. Someone has to sit there manually and glue these plates on at the moment. So there's a human cost associated with this. You might imagine it might be nice to develop a scalable process or a robotic process to actually do that kind of idea. And I'll show you some of those kinds of approaches later on. But anyway, this is something that's happening right now. So if you ever see this sitting outside, then you'll know that you've heard about this during this. It's called the AeroShark program now. Okay, so that's in air. Okay, I want to focus more on water, on fluid flow today. So just by way of introduction, now we're going to have, we have to think a little bit about liquid sitting on a surface. And so I'm going to have to do a little bit of math for you, okay? But I'm going to try and keep the amount of math to the minimum. And I'm just going to cover something called the Young-Laplace equation, which covers the idea that if I have a liquid sitting at a surface, then I have to understand that there can be a pressure difference between a curved surface and the other side of it. And so the general formula for the Young-Laplace equation is given here. It depends on the principal radii of curvature of the surface. The most common way is to think about a spherical bubble, because then the radius of curvature is the same. R1 is equal to R2, and then you get a result that looks like this. This is why bubbles in champagne pop. Okay, when you hear them pop, it's because the pressure inside is higher than the surrounding pressure. So I'm hoping we will get to practice this a little bit later on in the reception, okay? But you'll be able to, in some sense, tell the size of the bubble. Small bubbles pop with a higher sound than this, and a good champagne has a very small bubble. So this is the basic idea. The coefficient here is called the surface tension. And I've given you some typical ideas of values for these things here. So the surface tension of water is the one that we're going to care about, is about 72 millinewtons per meter. And that's a small number, but if I divide it by a small radius, this can give rise to a large pressure. And that's one of the things that we're going to exploit. So as engineers, we'd like to think about how can we change the radius of curvature? What can we do to change the shape or the structure of surfaces? And there are two important natural length scales. So one of them is called the thermocapillary length. Some of you will know about Brownian motion or Brownian energy, the idea that, that surfaces or that gas molecules have a kinetic energy that scales with kT. And so if I work out this number, the ratio of kT compared to surface tension, it comes out to be around 5 to 10 nanometers. Okay? So that means although I draw this as a nice smooth surface, in reality, if you were to look at it, it's actually got little waves on the surface that are about 10 nanometers in scale. So this is not an accurate drawing on the nanometer scale. It's also not an accurate drawing if I go on a big scale, because if I balance surface energy and gravity, I get another natural length called the capillary length, or if you're an American, the capillary length. So you can tell I'm an English person at heart when I say capillary. And this comes out to be about 2 to 3 millimeters. And you all know this, particularly on a Belgian day in winter, because this is the size of raindrops. Okay, so this is roughly a raindrop falling through the air. The gravitational fluctuations and surface tension mean that all the raindrops are in this kind of range. Okay, so notice that there's about 6 orders of magnitude between here. And that is great if we're an engineer, because it says that I can play with surfaces anywhere between the nanometer scale and the millimeter scale, and I should be able to change the Young-Laplace balance. Okay, so I should be able to change the pressure on a surface. And so I call this interfacial engineering. Okay, it's not chemical engineering, it's not chemistry, it's not physics, it's a little bit of everything, because it involves surface energies, it involves geometry, and we're going to play around with things in this kind of range of scales. So we've spent a lot of time over the last decade dealing with this, actually more than that now, almost 15 years. We started by trying to make oil repellent surfaces and looking at textured surfaces so that not just drops of water, but also drops of oil are fully repellent. And then we've also looked at things that are ice phobic, trying to make surfaces that are anti-icing so that you don't have to de-ice a surface. We've looked at fingerprint-resistant surfaces. You heard mentioned maybe yesterday, we've also looked at surfaces that will collect water from the air, what's called fog harvesting. And then we've also looked at coating these things on fabrics, and then also at gas hydrate surfaces as well. So I really like this old term, physico-chemical hydrodynamics. It looks like a really complicated term. You'll see this in the literature in the 1950s, but it really does sum up what's important. Physics is important, chemistry is important, and fluid mechanics is important. And it's a little bit of all three of those that we're going to care about today. Doesn't include the word rheology, I guess I noticed, but maybe by the end of it, we'll get some rheology in there as well. So today, I'm just going to focus on this idea of a drag-reducing surface. And in particular, this is a fabric that's been submerged in water. And you'll see that it looks shiny. You'll see that it looks very shiny. That's the trapped layer of air that's sitting in the surface. And biologists give this a name. It's called a plastron. And so nature developed this idea. The poster child for this is really the lotus leaf. If you've ever seen water on a lotus leaf, it looks shiny and silver, and that's the air layer that's trapped underneath it. The key idea, I'm not going to go into the math of it, but there's a relationship called the Cassie-Baxter relationship that tells you about how surface structure affects the surface geometry here. And the idea is that nature's very good at doing things on multiple scales. So it doesn't just build things on a nanometer scale, it can do them all the way up to millimeter scale. It's what you might call hierarchical. We're going to build things up from small scale to large scale. So we can't build something quite as good as a lotus leaf, but we are going to develop something that's almost as good, and we're going to be able to do it in a way that sprays on a surface coating. The other poster child are bird feathers, which are naturally very hydrophobic. And then I've also mentioned shark skin and shark denticles. So here I'm trying to show you some things at the biggest scale, on the millimeter scale. But if you look closer at the surface of a lotus leaf, you'll actually see it's got bumps on it. Okay? And if you look closer at the spray-on textures that we'll generate, they're going to have bumps on it. And if you look closer at a bird feather, you'll see that it has these little riblets associated with it. And if you look at a shark, you'll see that it's got structure. So we're now down from the millimeter scale to maybe the 100 micron scale. Okay? If you look even closer, you'll see that the bumps have bumps on them. Okay? And so there's even smaller bumps on the big bumps. And you'll see that the bumps that we make have a rough texture as well. And you'll see that these little side spines on here actually themselves have side spines on them. So nature is very good at this idea of doing the same thing again and again and again on different scales. And finally, when we get down to the molecular scale, you see that these little bumps are actually tiny little nanometer scale wax crystals. And so nature grows these wax crystals on the surface of a lotus leaf. We can't quite do that. We're going to use these nanometer size spheres that are made of silica and oxygen. And they have this lovely acronym POS. It stands for polyhedral oligomeric silsesquioxane. And I'm not going to say that again, okay? So we'll just call it POS, okay? But it's basically silicon, and for every silicon, you'll see that there's an oxygen. So there's a silicon at the corner, and there's an oxygen at the middle of it. And so these little molecules give me structure on the nanometer scale. So this is going to give us a way of going from nanometer scale all the way up to micron scale and all the way up to millimeter scale. So we're going to try and copy what nature does, but we're going to do it in a spray-on kind of way. Okay, everybody clear? So this is what I call interfacial engineering. It's a little bit of chemistry, it's a little bit of physics, and there's a little bit of fluid mechanics in actually putting the stuff on surfaces. Okay, so we want to be able to do this at scale. I don't want to stick things on the side of airliners. I want to be able to spray on them. So we've spent a lot of time dealing with electrospray systems. And so if I do this, this is just an automated spray system that is spraying these polyhedral oligomeric silsesquioxane molecules onto a surface in terms of a volatile solvent. And so this is a very scalable technology that we can, in principle at least, spray something the size of a boat. So that's the approach. Just to show you what we get when we do this, here's an uncoated glass slide, and here's a spray-coated glass slide. And so this has essentially a smooth surface, and now we've got this textured surface. And you might ask, what are the consequences if we put this in contact with water? So here's droplets of water. And you'll see the droplets of water don't run off because of contact line pinning, but here's how hydrophobic this surface is. If you use bubbly water, so you ask about air and water together, then you can see that the Coke gets stuck. You'll see how non-wetting this is to Coke on this surface. And if you're very messy, you might spill a viscous liquid on here. This is chocolate syrup. And you'll see that it drains very, very slowly because of the action of viscosity. But here's how non-wetting this surface is. You can see that all sorts of liquids will just run off. And this can be sprayed onto fabric or any other material like that. You can see it's not perfect. If you look very closely, you'll see small droplets stuck. And this is because there's a phenomenon called hysteresis. Okay? The advancing contact line and the receding contact line aren't quite the same. Okay? But these surfaces make very, very small hysteretic kind of levels of surface. And so all sorts of materials will just run right off this surface. Okay. If you're a messy eater, this would be very good because you can coat your tie or your shirt with this kind of material as well. And this is not just water, this is a very viscous material. Okay, so here's a technology that we've got that's scalable, that we can think about coating things. And what we're going to do is we're going to use this spray-on technology and think about the friction associated with it. So how this is working is exactly what I mentioned earlier on, this idea of making a hierarchical surface. Here's the structure that we get under an electron microscope. This is 100 microns in scale. And you can see all of these holes in the surface are where we're going to trap air. Okay, so there's going to be air trapped in this surface. Okay, to convince you of that, here's a nice approach of using a confocal microscope to do it, where we use a red dye in the polymer here, so that I can actually look at the material that's red is the polymer. Then I'll put a green dye in the water, and so if I put this underwater, I'll see green dye everywhere. But it's only where the water wets the polymer that you'll see both green and red, and that's where you'll see purple. Okay, so you'll actually see that most of this, there's no purple, and so almost all of this surface is actually air. Okay, so we would call that a three-phase system. It's got air and polymer and water above it. And that's what this Cassie-Baxter relationship, I'm not even going to write it down, but they thought about this as a way of describing what is the contact angle on a surface like this. Instead of writing down the equation, I'm going to show you a picture of what the contact angle looks like. So here's a drop sitting on the surface, and you can see that the droplet really doesn't want to touch the surface at all. The contact angle here is about 160 degrees. Okay. The one thing that I will show you is how low the hysteresis is, because I'm going to drag this surface backwards and forwards, and you'll have to look very closely to see that you can even tell that the droplet changes its shape. It changes its shape by less than 1 degree as you go from one direction to the other. And so it's almost perfectly frictionless, it looks like. Okay, you can see that the drop doesn't change its shape at all. There's almost no force on this drop. And that's because it's not really water on a solid, it's really water floating on air. For those of you guys who are doing fluid mechanics, you might remember something called the boundary condition that you apply at a surface. And essentially, we're not having a no-slip surface here. We're having a very, very slippery surface here. Okay? That should be good to reduce friction. That's what we want to try and do. Okay, so this is the surface. This is what it looks like. So as I show you things from now on, now you've got to imagine putting this on a surface and thinking about flow over the surface. Okay, and so here's this boundary condition that I mentioned. The thing that you've learned in fluid mechanics is the idea that where a surface of water touches a solid, we apply a boundary condition called the no-slip boundary condition. Okay. But where you have a surface of water touching air, we apply something called the no-shear boundary condition. So there's no velocity gradient. So what we're really getting is a mixture of these two boundary conditions. Okay, so there's a mixture of places where it's sticky and places where it's non-sticky. The characteristic length scale that's going to be important in what I talk about, and now I'm going to have to give you one more equation, is going to be something that depends on the density, the viscosity of the liquid, and the shear stress on the surface. And in fluid mechanics, this is known as the viscous length scale. So this is a small number. This happens to be about 5 to 10 microns, just to give you some idea of the range. And so this is going to be the characteristic length scale that we have to think about when we make these structures. Some of you may have heard of something called the Reynolds number. This is going to allow me to define a Reynolds number called the shear Reynolds number. And this is going to depend on the surface shear stress and on the density and on the size of the geometry. So I'm not going to have time to go into the details, but this is the important parameters that we're going to now think about. And because we're going to do this on average, then what we're going to do is we're going to average this over a surface. And we're going to think about how the slip length, the slip velocity and the slip velocity gradient are related to each other. And that's given by something called a slip length. So B is going to be an important parameter, and it's going to have units of length. So that's all you have to remember, is that B is going to have units of length. And what I'd like to do is I'd like to build a way in the lab that allows me to check this out without having to put it on a submarine and going out into the harbor and trying it. Okay, so this is where a rheometer is going to come in, because one thing a rheometer is really good at doing is at measuring shear stress. Okay, it's got a very, very sensitive transducer. And so maybe I can combine everything that I've told you so far with a rheometer and actually use the kind of rheometers that you have in the lab to actually measure the slipperiness of these surfaces. And so the geometry we're going to use is called the Taylor-Couette geometry. How many of you have used a Taylor-Couette flow before? Okay, so at least some of you. Okay, if you haven't, the way to describe it, here's two recent papers from the literature. If you're a physicist, then it's been called the hydrogen atom of fluid mechanics. Okay, if you ever learn atomic physics, the first thing you learn about is the hydrogen atom, right? It's the simplest thing. Okay, the simplest fluid mechanical flow that we can think about is called the Taylor-Couette cell. It's just one cylinder inside another cylinder. Okay, no sharp edges, no ends. It's infinitely long. If you want to think about how long this problem has been thought about, this drawing is actually from 1667 from Newton. Okay, this is in the Principia. Okay, so even Newton knew about this, this flow a long time ago. If you're more of a biologist, however, it's also been called the Drosophila of fluid mechanics, okay? Because what do you study when you do biology? You study the simplest thing, which is either a nematode or the Drosophila. And so it's also been used as to think about as a way of understanding flow instabilities. And I'll show you some of those in a minute. But as you spin the cylinder faster and faster, you'll start to see transitions and flow instabilities. Okay, so now everybody, you can, whether you're a physicist or a biologist, hopefully it gives you an idea of why we're interested in this geometry. And it's a really remarkably simple geometry, but it's got remarkably complicated physics that we can understand in here. So from this review article by Detlef Loser from a couple of years ago, there's a very nice drawing of all the different kinds of things that have been known, depending on whether you spin the inner cylinder or the outer cylinder or both of them. And so here's a map of all the different kinds of things that can happen just in this one geometry. Okay. So, and so all of these are different domains that are known. The one we as rheologists like is the one that's called the Couette flow range, okay, where the fluid mechanics is very boring and we can understand the complicated nature of a fluid, okay. You'll notice that there's two Reynolds numbers on here. One is for the inner cylinder, one is for the outer cylinder. Okay. The way most rheologists use it and the way I'm going to use it, we're not going to spin the outer cylinder at all. We're only going to spin the inner one. So we're really only interested in the flow along this axis. Okay, so no outer Reynolds number. But as we crank up the inner Reynolds number, we'll find that the flow is it becomes unstable. Rheology ends right at this point, okay, because now the flow becomes complicated. And you'll see that there are waves, then there are modulated waves, then there are turbulent vortices, and eventually we're going to end up in fully turbulent flow. And so that's where we're going to go, is to boldly go where no rheometer has gone before. Okay, which is into the ceiling, okay? So we'll get to Reynolds numbers that are more than 10 or 100 times this. Okay, so if you like mechanical engineering, if you like design, then what we've built is a system that will allow you to connect this to a rheometer. The rheometer can measure the rotational speed and the torque very, very accurately. When you put this on the rheometer, it looks something like here. We're spinning the inner cylinder. Here are the Taylor vortex cells that you can see, okay, inside. And we've built this inside a viewing box so that you can get good images of it as well. If you want some idea of scales, the gap is about 12 millimeters, okay, in terms of the scale of the thing. And the range of Reynolds numbers that we can get to is up to about 100,000, okay? Anyone who's a rheologist here is horrified at this point, okay? Because normally we like Reynolds numbers to be less than 1, okay? But that's not going to be useful for us, and we're going to crank this up. The shear stresses are actually remarkably small. They're still only tens of pascals, so that's a very small stress, but it gives you some idea of the range of fluid mechanics that we're going to achieve. And now the rotor is something that we can put our coating on. Okay, so all these different coatings that I've described to you, we can put on there. And we're going to crank up the Reynolds number, and we'll see all of these transitions from a smooth state to a Taylor vortex flow, a wavy Taylor vortex flow, turbulent vortices. And eventually, we're going to get into a region where you don't see anything, and that's because the flow is fully turbulent. And that's the region that we're interested in if we're interested in drag reduction. So most of what I'm going to show you is going to be above a Reynolds number of 15,000. Okay. All right, so here we go. Here's our coating. Here's what the flow looks like in the rheometer. You can see that it's a very complicated flow. The coating, when it's sprayed on, it had very low contact angle hysteresis. So you can see that drops just run right off the surface, almost no friction. If you lower the surface in, you can see that it looks shiny. You see that this looks silver. This is the plastron. That's the air layer that we're trapping. If I pull it out, the surface comes out essentially completely dry. There's almost no hysteresis. And so even though you think it got wet, it didn't really get wet at all. Okay? It really just trapped a layer of air. And we're going to be able to see the onset of turbulence very easily because the rheometer is very good at measuring torque. And we'll see a change in the slope or the scaling of the power that's required when we get to the Reynolds number that's associated with turbulence. And so for this rheometer, for our design, it's at around about 15,000 or so. And so beyond that, we're going to be in the turbulent regime. So this is where a rheometer is kind of a useful thing because we can measure the speed and the rotation very, very accurately. Okay, everybody get the idea? Okay, so we're going to measure the torque. It's not quite zero, but we'll see if it changes when we put this coating on or when we don't have a coating on. Okay, so I'm going to plot this in a particular way that may look strange to you to start with, but it goes back to two very famous people. If you're a chemical engineer, at least, you've all heard of Prandtl. Okay, if you're an aerodynamics engineer, you probably have heard the name von Karman as well. And so we're going to plot the results in a way that was first talked about by Prandtl and von Karman. I'm going to plot the friction, but I'm going to plot 1 over the friction, what's called the skin friction coefficient. And I'm going to plot that as a function of this Reynolds number, the shear Reynolds number. And what they showed is that when you do it this way, you actually get a linear relationship. Okay, so notice that some of you will have heard of the skin friction. If I take 1 over this and I take the square root of this, this is a measure of speed. And here is the shear stress, and this is a measure of how much force I have to put on the surface. Okay, so here's a nice picture of Prandtl on von Karman. 2 other names that you may know. I don't know if we have any Chinese graduate students here, or anyone. Does anyone know the name Tian? Okay, no, he went back to China. He really, I probably said that wrong. Can you say it for me? Yes, yeah. So he was a professor at MIT. He did his PhD with von Karman. He essentially was, and unfortunately in the days of McCarthy, he was sent home from America because he was suspected of being a communist, and started the Chinese ballistic missile program. But in these days, he was a student worker with von Karman. And so here we have China and the US. Von Karman was in the US. Prandtl stayed in Göttingen. Okay, and so this is the amazing thing about this picture is you'll notice that 3 of them are in military uniform. 1 of them is not. Okay, this is because Prandtl is under house arrest. This is at the end of World War II. And von Karman had been sent back to essentially arrest Prandtl or to investigate what had been going on in terms of German fluid mechanics during the Second World War. So for those of you who are graduate students, imagine coming back and arresting your PhD advisor at some point. Okay, but it's a wonderful picture outside the fluid mechanics lab at Caltech. But the main thing we're going to care about is their way of plotting the results. Okay. And the key thing we want is we want a linear relationship. So there's 2 coefficients to measure. As I mentioned, what you're going to see on this thing is how fast I go. What you'll see on this axis is how much stress it costs me or how much friction I have. And so they worked out that, what we'll find is that you'll have 2 coefficients that we have to measure that tell you about the slope and the intercept. They're not important. They're just the coefficients that tell you about a linear relationship. Now, if we have a no-slip boundary condition, this is what you get. The question you might ask is, what if I have a slippery boundary condition? So we've extended that theory to a slippery boundary condition. And in addition to these coefficients m and n, there's one extra term that shows up that depends on how big that slip length is, which is b in millimeters or microns, compared to how big the gap is. So Jan, I know you've spent a lot of time talking about slip. Here we want to make the slip as big as possible. And I think you were telling me yesterday this is something you're interested in doing now. So how can we tell this? Well, we can see how that is by essentially plotting our data in these Prandtl von Karman coordinates and seeing if they lie on this line or if they lie above this line. Okay, so that's what we're going to do. And here's the data for our spray-on surface. And what you'll see is that at a given Reynolds number, we actually have a lower friction. And a lower friction means I go faster. Okay, and so I'll get a point that's above this curve, and this green line is a fit to this, and so it tells me that the slip length is about 11 microns. Okay, so we're sliding along this surface with a slip length that's actually relatively big by rheology terms. This corresponds, for those of you who don't care about slip lengths but care about drag reduction, this is a 22% reduction in drag. Okay, so at a given force, I go faster, or if you prefer to think about it, at a given speed, I'll use less stress to do it. So either way, we lie above this curve, and so in some sense, we've achieved the problem. And now the relevant dimensionless parameter that we care about is how big can we make this quantity. Okay, so as design engineers, you can think about, what about changing the molecule? What about changing the spray-on size? What about changing the size of the roughness? And those are the kinds of things that we're going to explore. And we've done that for all sorts of different kinds of coatings. And I'm not going to bore you by showing you all of them, but just to say that we've looked at this spray-on technology. We've looked at sandblasting, really torturing a surface by sandblasting it, etching it, and then acid etching it. We've looked at putting fluorosilanes on surfaces, and we've even looked at putting grooves in surfaces and then putting texture on side of those grooves. So there's many different ways of doing this. All of them are doing what I told you about at the beginning. They're changing the boundary condition at the surface, okay? On scales between the millimeter and the micron scale. That's the kind of range that we're interested in. Okay, what I'll just show is a couple of results. Here's this tortured surface where we first of all take aluminum, you boil it, then you put it in acid, and then you finally put a hydrophobic coating on it. The nice thing about this is that you might call it a subtractive process. The spray-on one, I have to add something to the surface. Here, I just take a metal surface and I remove stuff from the surface. Okay, so this is a subtractive process. And what you'll find is that when we do that to our rotor, we'll find that we go even faster, and the slip length is now as big as 30 microns. And that's because there's air trapped in all of these holes between this etched surface. Again, if you don't care about this, if you care about drag reduction, we can get up to about 28% drag reduction. And this works both in fresh water and slightly less in seawater, and that's because the surface tension of seawater is a little different than the surface tension of fresh water. However, you'll notice one thing about it. This looks like it's getting better and better and better, and then you'll see that the drag reduction starts going down. Okay, so if you're looking very carefully, you might say, well, it looks like your data is beginning to deviate from your nice theory lines here. Okay, so what's going on there? Okay, that's the next thing we're going to think about. What we'll find is that the turbulent fluctuations are beginning to push air out of these surfaces. And I'll show you that very dramatically here. This can happen even if you don't have a flow. If you put air in a cavity and you just wait long enough, eventually that air dissolves into the water. Okay, so we know that air has quite a good solubility in water. And so eventually our nice plastron that we have, our nice bubble of surface, just disappears, and eventually the surface is fully wetted. Okay. What this looks like in terms of our rheometer looks a bit like this, is that we're going along, we're shearing the material. For the first 4 hours or so, things are fine. And then suddenly you'll see that the drag increases, or the wall shear stress increases. And what you'll start to see is that the surface is starting to get wet. Okay. The best surface that we can make, this spray-on surface here, you can see that it happens, and it happens over the period of many, many hours. Okay, so after 16 hours, there's still a little bit of drag reduction, but it's nowhere near as good as the beginning. Okay. Now, if you don't have to live for more than 16 hours, think torpedo or something like that, then you don't really worry about this. But if you're thinking about a boat that's cruising across the ocean, this is a big problem, is that the first day you go faster than you do on the second day and things like that. So this is just an illustration of how important these ideas are of things that go wrong, like fluctuating pressure, shear degradation, various things like that. There's plenty of room for engineers to improve on this. I'm not going to say we have a solution, but I'll show you some solutions that we've thought about. And what we're going to need to do is we're going to need to spend some energy. We're going to need to be active now about things, not just passive. So what we want to do is we want to think about ways of keeping air near a surface. Nature has thought a lot about this. Here's nature's active drag reduction system. If you watch or read National Geographic or look at BBC videos, you'll frequently find demonstrations of this. A penguin, which has a hierarchical feather-based surface, will dive extremely deeply and trap air in the surface. And what it will do as it comes up to the surface is it comes up so fast that the bubbles it actually looks like the penguin is boiling. Okay, and what that really is just decompression of the pressurized air on the surface. And this is nice. It gets what's called a bubble boost. Okay, so it gives you an extra thrust, which is extremely useful if you want to get out of the water and onto an ice floe, particularly if you're being chased by a killer whale or something like this. So this is nature's way of actively producing bubbles in a wake and lowering friction. So we might like to try and think about, can we do something like this? So we have a plastron, but then we're actually going to try and inflate that plastron. So one way we can do this is using something called the Leidenfrost effect. We can heat the surface. And many of you may have done this. If you've ever done this with a hot frying pan, you might have dropped hot water on a frying pan and seen the droplets run across the surface. And essentially what we're using boiling, very local boiling, that anywhere the droplet touches the surface, we actually are going to boil the water. And so what we want to do is we actually want to take our couette cell, and instead of doing it at room temperature, we're going to boil our couette cell. And now you'll actually see, if you look at it, you can see the plastron on the surface. You can see that there's an air layer on the surface. The important thing about hydrophobic surfaces is that they lower the requirement of what's called the Leidenfrost temperature. For those of you who are engineers, you only have to go to a few degrees above the boiling point of water to do this. So we're going to use this as a way of trying to get the Leidenfrost temperature down to about 105 degrees. Okay, so how do we do that on a rheometer? Well, what we want is we want to make our couette cell hot, put it in a cold fluid, and then locally boil the water next to it. So we did this. For those of you who are rheologists, you would like this. We did this by using a rotating layer of mercury or a metal alloy here, so that we could get a very low friction way of actually getting electrical current into the system. But now when we do this, we can actually get drag reduction that's as high as 80 to 90%. Okay? And the reason is because the viscosity of water vapor is much less than the viscosity of water itself, by a factor of more than 100. So we can now get almost 90% drag reduction, and the slip length is as large as 1 millimeter now. Okay? This looks fantastic. Okay? Until I tell you that we have to put about 100 times more energy in to boil the water than we save by a friction reduction. Okay, so we're not really saving energy, but we're taking energy from one form and putting it somewhere else. Okay, on aircraft carriers and on large marine vehicles, there's a good source of hot water because they all use steam boilers. For those of you who are chemical engineers, you'll know that waste heat is something you typically have to reject. And so here's a way of rejecting waste heat out of the surface and getting some friction reduction out of it. So there's a possibility at least, but certainly at the moment it's not an energetically favorable way of doing it. But it works. Okay, so here's another way of doing it. Instead of using thermal energy, let's use chemical energy. For those of you who are chemical engineers, you learn about the chemical potential and the idea that, I have a potential to do something. So we're going to take hydrogen peroxide, and we're going to use hydrogen peroxide to, again, locally generate oxygen near the surface. Okay. Here's a nice model textured surface of posts on a surface with a platinum catalyst. This is definitely not a scalable surface. You couldn't put this on a surface of a submarine, but I'll show you that it works. Here's one that is scalable. This is a laser pattern surface with a manganese catalyst on it, which turns out to be a good way of doing it as well. And if I play these videos, if they'll play, what you'll see is that you'll see that the surface will generate air, which is these shiny regions that you'll see appearing. And the nice thing is this is a self-limiting reaction, because the only place where you get catalysis is where the water touches the surface. That produces gas, lifts the meniscus off the surface, and then the reaction stops. And so you'll see that, that the surface essentially generates a nice shiny air surface so that we can get back to this nice hydrophobic coating as well. So this doesn't require thermal energy, but instead it requires chemical energy in the form of a peroxide bond. And what you'll see is that we can go from a low shear stress, we can induce wetting so that the stress goes up. Then when we add a little bit of peroxide, you'll see that we get some recovery, so the friction goes down again. So we can switch from a low friction to a high friction and back to some partially recovered surface. It's not perfect. You can see that we don't get back to where we start, but at least it demonstrates this idea in principle. Okay, so how am I doing on time, Christian? Fine so far. 15 more minutes, perfect. Okay, so what I've shown you now is passive surfaces. I've shown you active surfaces, but I promised you polymers as well, and I haven't mentioned a polymer really at all yet. So we're going to come from thinking about superhydrophobic surfaces and plastrons to now thinking about polymer injection. Okay, so we now think about not changing the surface, but changing the flow or the fluid mechanics of what goes on around here instead. And this is something that actually has been done on large scales. So this is a British Navy character in the 1970s. And what they did is they modified the hull at a certain point so that they could inject polymer in the boundary layer of the boat. And what they found is that by just taking 10 parts per million of a particular polymer called polyethylene oxide, that you could get 12% reduction in drag. Okay, so this works, okay, but you have to continuously inject polymer into the boundary layer of a boat. Okay, turns out that this is not commercially feasible. It's too expensive. The one place where this does work commercially is if you're dealing with something that's much more valuable than water, and this happens to be true in oil pipelines. So polymer drag reduction is used in the Trans-Alaska pipeline. You may have heard of this. It runs 800 miles across Alaska. And by adding a little bit of a high molecular weight polymer, it's a polyisobutylene, if you put that in, then you'll actually find that you can increase the flow rate through the pipe without having to increase the pressure drop. Okay, so you can get 1/3 more oil through without having to change the pumps. That's bang for your buck. Okay, that's worthwhile, and that's because of the cost of oil per gallon. Okay, so this does work. Here's another application. This is a demonstration that was done in the 1960s of a fire hose and how far a hose will go. And then if you add a little bit of polymer to the hose, you'll find that actually the water goes much, much further. And so this would look like a great application. This means that you can use a fire hose and spray something on the 7th floor instead of just on the 3rd floor. If you're interested at the end, I'll tell you why this didn't work, okay? And it was a marketing issue. Or maybe there's a question here.
If they were so worried about this pipeline friction, why did they put so many geeks in it?
Yeah, that's a fantastic question. Yes, yeah. So it turns out, yeah. So the question is, why would you put kinks in this? And so that's generally set by the presence of rivers and other geological features. On large scales like this, the Reynolds number of the flow in this pipeline is not so high that the minor losses are important. So the minor losses compared to the major losses are tiny. Okay. There's 40 pumping stations across the Alaska. So you basically pump and then you go up to another one. Most of the pressure drops and the costs is in the linear or the major losses rather than in the minor losses. I thought you were going to ask me, so this was the trade name that was given for it, slippery water, okay? And the idea was that you'd be able to put out fires over a much greater distance. Okay, so the principle is shown in the following. So here's some nice flow visualization of what's going on. This is using something called Schlieren imaging, which some of you may have heard about. But instead of using thermal Schlieren imaging, this is actually the fact that if there's 10 parts per million of a polymer in a flow, then the refractive index is different than you would have in pure water. So here's a Newtonian jet entering water. You can see the onset of instability and the development of turbulence. And here's a polymer entering water. And this is just 50 parts per million of polymer. And you can see that the flow becomes unstable earlier. But you can see that when it becomes fully turbulent, it looks rather different to that. Okay? Understanding those differences is something that we're really interested in from a fundamental point of view. I'm not going to have time to tell you too much about it now, except to say that if you look at the power spectrum of the fluctuations, this is the classic Kolmogorov result, is that it depends to the 5/3 power of the frequency. This is if you measure the fluctuations right here. When you do it with a polymer, the fluctuations die off much more rapidly with the -3rd power. So there's much less energy in the turbulent fluctuations here. Okay, where did the energy go? It went into stretching polymers. Okay, it went into stretching polymers. And you can see that by maybe taking a Fourier transform of this, a 2D Fourier transform, and you'll see that the parallelogram is much more oriented, much more elongated, because you're stretching molecules. Here, there's no molecules to stretch. Okay, and so this is the underlying fluid mechanics of turbulent drag reduction, is that we change the amount of power and we change the stretching that's present in the fluid. So this is what we're going to use. We're going to try and use this to reduce the friction on a surface. I mentioned the key impediment so far has been the cost of polymers. Okay, synthetic polymers cost quite a lot to make. And so people have been looking around for the last 2 decades trying to find different biopolymers that might be good ways of doing it. So here's a number of different ones that have been used. Some of you may have heard of some of these. All of these are too expensive as well. Okay, so these are too expensive. However, there are some even cheaper polymers around. And for any of you who are vegan, you may have eaten flax, or you may know these other high fiber foods. If you cook with what we call okra in the United States, then you will have seen this as well, that when you cut an okra open, there's a high molecular weight polymer that's released, and it's generally known as mucilage. Okay, so this is the term that's used, and this is what we're going to focus on. Okay, so this word mucilage comes from the same origin as mucin, okay, and mucus, and all these kind of sticky, goopy fluids that I like to play with. Okay, and it's a natural thing that's available, and it's much cheaper than synthetic polymers. So mucilage has been around. It's what they used to make the back of stamps. If you've ever licked old stamps when you used to put them on, this was the material that was on the back of them. Where Christian and I first became aware of them was in plants like the sundew plant, which actually secretes this polymer. And this is what, of course, traps unfortunate animals that get stuck to the surface. So it can be used as a defense mechanism. The hagfish is another one in nature that uses these kinds of materials. And it forms a very highly stretchy, gooey material, okay? Which is what we want. We want to stretch and reduce the turbulent fluctuations. And so we've investigated this as a drag-reducing possibility. This is what the molecule looks like. So this is what is in flax. The particular material is this polysaccharide called an araboxylan, and it's got a molecular weight over 1 million grams per mole. So it's very high molecular weight. And literally all you have to do is you just have to put a seed in hot water, okay, for this to happen. So here's a seed. We're going to use our same Schlieren imaging system. And essentially nature has packaged everything you need in a flax seed, okay? You take this, you put it in water, and you wait. And what you'll find is that it slowly dissolves. And you'll find that the polymer starts to come off from the surface. It's slightly denser, which is why it's draining here, okay? And this is just, this is time lapse, so it takes a few tens of minutes for this to happen, but you essentially generate a nice high molecular weight material almost for free, okay? By the end of it, after 80 minutes, you've actually almost gelled the entire sample that you have in there. And so you can also see that there's air trapped in this, and so it also produces air in the surface as well. And so this is essentially the material that we're going to use for some drag reduction. And you all know how to do this experiment now. Okay, we take our Taylor-Couette cell, we put it in water, we have our baseline in these Prandtl-von Karman coordinates. We remember that how fast I go is on this axis, how much shear it costs me is on this axis, and we measured these coefficients before. And what we can do now is we can just put some flax seeds in and see what we get. And you'll find that if we do it with polymer, we have a new line that's faster. And remember, we're going faster at the same Reynolds number, so that means that it's costing us less energy. And if we do this with flaxseed, then we'll find that we actually go even faster. So we can actually get 30% drag reduction at just around what's called the critical polymer concentration, or C star. So for those of you who are polymer people, but so we'll get about 30% drag reduction out of doing this. Okay, so we've spent a lot of time exploring this for different molecules. As you change the concentration, you'll find that you get more and more drag reduction, and essentially you approach something called the maximum drag reduction asymptote. And what you make when you look at the polymer is this kind of sticky, stringy, slimy polymer solution, and it just comes from essentially putting flax seeds in water for 30 minutes. You can all do this at home. Go down to Whole Foods, buy some flaxseed, do this tonight, and you'll make this strange, viscous liquid. Okay, so all we have to do, you take about a 1 to 800 dilution, turns out to give you a concentration in this range. And it's about as good as a synthetic polymer called polyethylene oxide. Okay, so we'll get between 20 to 25% drag reduction. But you also see that over time, it also decreases just like polyethylene oxide does. It breaks down because of shear, okay? And so we can't stop the chemical degradation, but we can get almost as good drag reduction even at relatively high Reynolds numbers. But here's where it wins, okay? If you have to buy polyethylene oxide, this is roughly the cost of it, whereas the cost of flax seeds is about 2 orders of magnitude less, okay? Now, most of the flaxseed isn't something that we want. We have to throw that away. It's only the coating. But here's what the cost calculates to make 1,000 liters of solution. It costs you about $7 to do it with a synthetic polymer. It costs you about 40 cents to do this with with a biological polymer. So again, more than an order of magnitude cheaper. And so again, we're stealing the ideas that we've learned and using them to make something that's much cheaper. Okay, so in the very last slides that I'll show you, if you're thinking about this and you're an engineer, you might say, well, he did one thing which modified the surface boundary condition. He did another thing, which is he said, well, let's not measure the surface, let's change the drag reduction by putting something in the bulk. Okay? Those two are independent, okay? So maybe the right thing to do is to add them two together, okay, and see what we can get out of it, okay? And so that's the last thing that we'll do. We'll take our hydrophobic surface that looks like this. Remember, that's modifying the boundary condition. Now we're going to change the rheology of the surface. We're going to put in this nice viscoelastic polymer that makes this strange viscoelastic liquid. And essentially, we've now got polymers in the bulk, and we've got a modified boundary condition on the surface. What do we get? Well, they do indeed add together. We can get both of these effects will give me drag reduction. But you have to remember how to add. And we have to add in this special set of coordinates called the Prandtl-von Karman coordinates. So we have to add together the slip length that we get from our superhydrophobic surface. And so here's water on a superhydrophobic surface. Then we have to add together what we get from the polymer. In this case, it's a polymer called polyacrylamide. So we add that and we add that. And when we add them together, we get the green line, which is shown right here. And so indeed, as long as you add in the right system, you add the slip length to the reduction in the polymer, and we get even more drag reduction. And I think that brings me just about to the end, okay? So what have I shown you? Okay, I've shown you that friction reduction is possible at scale, okay? This is not using lithographic surfaces. This is not on something the size of 1 centimeter by 1 centimeter. This is something that can be done now on the size of an airplane or on the size of a boat, okay? The key issue that still remains is how long do these microstructures live, okay? That's where engineers, that's where we have to work on as engineers, is extending the lifetime of that. I've shown you that you can get drag reductions with these kind of etched surfaces that are up to something like 20 to 30%, and the slip length on the scale of 30 microns. I've also shown you can get up to roughly 30% with biopolymers that are just as robust, no more robust, but about as robust, but they're 20 times cheaper. Okay, so that's where we are at the moment. I think the first place that you will see this is on cargo planes. Eventually, you'll start to see it starting to appear, I think, on other forms of transport as well. And so I'm going to end by just thanking the team of people who actually did this. I mentioned yesterday, research is a team sport, okay? I didn't do any of these experiments, okay? I played with the fluids and came up with some ideas, but these are the students who did all of the work. My longtime collaborator in chemical engineering, Bob Cohen, is someone I'd like to thank a lot. And then we've had support from the US Army, the US Air Force, and the US Navy. So we've kind of covered, the only thing we haven't had is the Marines so far, okay? But you can see the kind of places where this might be of interest. And I think with that, I'll say thank you for your attention.
Thank you, Gareth, for a very inspiring talk. We have time for a couple of questions, but bear in mind that the more you ask, the longer we have to wait for the reception that is going to follow afterwards. Two stores upstairs, the Saal Couvreur. But anyways, if other questions, please fire away.
You just discouraged all questions, you realize?
Well, I mean, for me, you kept actually the most important question was the cost analysis, and then you came up with that on the very last slide there. But still, for me, the question is if you would apply this now to a marine ship, I mean, how much of these flax seeds do you then actually need for like a typical journey across the Atlantic?
Yes. So I couldn't tell you I don't remember the exact numbers for the volumes, but it. You keep that one and I'll use this one. How about that? But it is viable because you don't actually have to keep the flax seeds. What you can do is harvest it and lyophilize it. So you can actually freeze dry it and you can take the polymer coating off it. So you'd soak the flax seed first, you'd essentially freeze dry the polymer and then you can use that. And then you would essentially just dissolve the polymer in warm water. Where do I have warm water? Well, the waste heat exchanger from the boiler. So in principle, it's possible.
And then it's just simply injected in front of the boat and then runs
in the boundary layer. Yeah. So the reason longevity is not such an, I'll stand back a little bit. Longevity is not such an issue because the only lifetime that you have to have is the residence time in the boundary layer. The residence time in the boundary layer depends on how close you are, but based on the buffer layer, it's about 100 seconds. So after 100 seconds, the polymer has been swept away from beyond the boat. Okay. The lovely thing about this from terms of biodegradation is that all I do is put sugar into the ocean. So as it breaks down, the polysaccharide will degrade and there's nothing added except sugar molecules. So I think it's both green and affordable, I think. Jan.
Yeah, thank you, Gareth. We, of course, think about this in terms of a kinematic boundary condition as we're trained from fluid mechanics. But as you go to complex texture surfaces, would it help us to think about it in terms of a stress boundary condition, with part of the stress being transferred to the solid, to the gas phase, we have a very complicated porous flow. So would that be a path forward to help us understand what the ideal topography should be?
That's interesting. Certainly, I think we move in that direction by always choosing to plot stress on the horizontal axis and really using RE sub tau, as they call it. So the Reynolds number based on the wall shear stress. We certainly don't understand the local distribution of stress. That's something that computations can get you, but we're going to plot it in terms of an average stress. And so, of course, as a rheologist, we take that by taking the torque, dividing it by the area. I will show you one slide that shows you how complicated these surfaces look like. People haven't got to doing simulations of turbulence with rough surfaces yet, but people have got, this is from Ali Mani at Stanford's work, to simulations of periodic surfaces. And the contour plot there shows you the magnitude of pressure fluctuations. And you can see that the pressure fluctuations are 10 times the average. And so you can see that the big pressure is always on the front of the surface, and then there's a negative pressure. Every time you slam into a post, you get this big pressure spike, and then there's a negative. So this is what causes degradation of surfaces, but people have not yet got to simulating rough surfaces. But what it does change is it changes the scaling as a function of how big the slip length is compared to the viscous length. And you'll see that instead of this nice linear result, you go to a 1/3 power law. So it gets worse the higher the Reynolds number you get. But I think indeed that's the right thing, is to think about stress as important at the surface.
More questions?
Yes.
I'm coming from the biomedical engineering field. So I was wondering whether some of the principles on drag reduction are also applied somewhere in our body, because you have quite some fluid flow in our body going on as well. Don't know whether you know something about that.
Yes, there's actually several people who have looked at using this. The polymer molecules like aloe vera or aloe have been used as potentially they're biocompatible and locally lower blood pressure if you're dealing with high blood pressure and you want to control flow rate as well. So anything that's biocompatible that you could inject or dissolve in the bloodstream certainly will. We have not worked at that. There are several groups, particularly a group at the University of Pittsburgh, that have looked at that a little bit as well. So I think there are possible ideas for that. Low friction coatings are used, for example, in stents and other materials like that as well.
Okay, thanks.
So you talked mostly about drag reduction as applications, but you also showed application to textile, where presumably it's more about preventing the soiling or the accumulation of all sorts of things we don't want to stick to our clothes. So can you say a little bit more about that? You also showed that it's not quite perfect. So does it mean that we still may need to clean our clothes in the end, or is there a way to use a different mode of cleaning? Because washing may not do the job because they're water repellent, right?
So great questions. I have a separate talk on that. We had a lot of work that was funded on looking at fabrics and uniforms in particular. A particularly challenging one is oil or oil-based systems. Jet fuels are incredibly low surface energy. The interesting question for all of you to think about is, how do you wash your clothes if they don't get wet? Okay, so if you have if you've done a really good job and you've got a totally hydrophobic surface, you can't wash your clothes anymore. Okay, now you might say, well, I don't need to because they never get wet, but of course they still get soil and dirt and things like that. One answer is supercritical carbon dioxide. For those of you who learn about phase change, okay, it's a fantastic natural dry cleaning way of doing things. So you use high pressure carbon dioxide. You wash your clothes in high pressure carbon dioxide, you drop the pressure, and they spontaneously dry. The challenge is actually that after one washing, it's not quite as good. After two washings, it's not quite as good. The degradation is still there. So after about 10 to 20 washings, you'll find that the coating is starting to be removed. So again, the challenge is longevity. But if you're dealing with use once and disposable things, then these kinds of coatings are used. For example, Tyvek is a great example of a textured substrate that DuPont developed that has a hydrophobic component as well as texture. So if you like really expensive hiking clothes, there are really expensive hiking clothes that are made that are non-wetting as well. So they do exist, but they do wear out.
Then maybe one final question from my side. Talking about fouling of your texture surfaces, and then in the last slide, putting a polysaccharide close to this, isn't that asking for trouble?
Well, in terms of promoting growth?
Well, I mean, aren't you eventually just filling your cavities with your degrading polymer at the surface, and then?
Yeah, I suppose in principle that could be a possibility. The good thing is that the high shear stress in a turbulent flow actually helps keep these surfaces cleaner than they would at rest. So I think Christian's referring to biofilm forming or biofouling. Anyone with their teeth knows about biofilms that form. You get this film that if you don't brush your teeth. But high shear stress is actually a good way of removing that. So actually the turbulent flow actually helps keep these surfaces cleaner. But yes, that's definitely biofouling is a challenge.
All right, I think then with this we can close. So kids, brush your teeth.
Kids, brush your teeth.
Final words, especially after having a very nice reception then as mentioned on the second floor. But first of all, let's thank Gareth again for a very inspiring talk. And with that, I would like to invite you all to the reception later on. Thanks a lot.
Thank you. I look forward to chatting upstairs. Yeah.
All right. Well done.
All right. Thank you. Thank you. Thanks for the question. Thank you.
maybe it's a stupid question, but would there be other ways to recreate the air layer that would not be as, because I was thinking something like ultrasound or some
Yep.
more targeted.
Potentially, that would be very targeted. The question is, how do you do that over a broad area? But electrolysis is a particularly good one. So the nice thing about seawater is it's quite conductive. So you can do this by applying an electric field as well. There, you're basically using electrolysis to split seawater. The challenge is the potential difference that you need. You need quite a large voltage applied to a surface. But the ones we've explored are chemical and thermal, and there's a group at LA that's looked at electrical energy. I don't think anyone's tried ultrasound over a broad area. But what ultrasound can do is it can generate very small bubbles, right? Cavitation bubbles. So if you knew where there was a defect,